Okay, hello everyone. My name is Shoudong Yang. Today, this video, I will give the presentation. I will talk about this paper, a general model for minimizing age of information at network edge. This paper is published in the IEEE Infocom 2019 from this group, these authors. I will introduce the outline of my presentation. I will give this background and a very brief, very simple motivation, and introduce this method on this paper. What the author did, and the final part is the experiment. They do a simulation. So let's dive into this paper. We will start with this background, introduce this background. And as we know, today we have a very huge network in the world. It's like a cloud, and in the wireless channel, we have this base station. It will interact with this all kinds of source nodes, and it may have some delay to send the information to this base station and to do this communication. So because this is the edge nodes, source nodes, so this part is called this network edge, because we know this network is very complicated, and this source node is every end to connect, link to this cloud, link to the net. So this part is the edge of this network. So in the basically the data collection is very critical in all, of course, in every part of this network, but it's also very critical in this network edge, because the applications, for example, in our phones, they depend on the timeliness of the sampled information. So for our source nodes, our phone, and the base stations, they need to forward the freshest sample to the edge, to each other as soon as possible. Then the researchers define this new concept, AOI, age of information. It quantifies the freshness of the information. Basically, it's if we give it a clear definition, it's the elapsed time for a sample. It's equal to the current time, subtract the time when the sample was first generated. So I'll give this example. A sample K generated at this time, and current time is here, is now, so it's equal to this now subtracted K. In the previous work, the authors mentioned that previous work, the previous works, they only consider simple cases. For example, for sampling, they only consider the time to generate the sample. They only consider the per time slot sampling. For the time slot, they need, because they need to send the data to the base station and receive the response. So it's they will do this sample by this time slot. Per time slot sampling, which means they will do the sampling operation after every time slot. And they also consider the case of 1 unit of data in each sample, and also channel transmission capacity is 1 unit of data in each time slot. So it's a very simple case. It's a very it's easy to solve this under these cases. In this paper, the authors consider more general cases. They can use, they define different sampling methods. They can do the arbitrary sampling or periodic sampling, and also per time slot sampling. And in real world, because source nodes, phone or other nodes will have different sample size collected from each source, so they also vary the sample size, and the base station will also have different transmission capacity. So this paper, they have a more general model. Based on this general model, the authors they design the scheduler and derive the theoretical lower bounds, which is the minimum age of the information. Okay, the sampling method, because in previous slides it shows there are 3 sampling methods. Arbitrary sampling, they may sample with different time slots. We can't predict the sampling. It's arbitrary sampling. And more general case is the periodic sampling. Source node I will perform sampling at every Ti time slot, and different source nodes will have different Ti. The third one is the per time slot sampling, which means the Ti equal to 1 for all nodes. And I will introduce some basic concepts. Each node I, for example, a phone, it will consist of Li units of information at each time, and only after all units of the sample from the source are transmitted to the base, it sends all units or the sample to this base. Then we say the base station has received this sample, and also the remaining unfinished units must be transmitted. Firstly, it must be transmitted before any new sample. For example, if we start transmit a sample at this time, then some new data generated, but the node and the base station need to finish this transmission before transmit other samples. Okay, then we go into this formal definition part. We will learn some notations. For source node I, we define this UIT is the generation time of the most recent sample at time slot T. Then the ASIT, here the S is the source node, equal to the T current time subtract the generation time. So current time maybe is here T, and the generation time maybe is here. It's sampled here, the U, so it's the age. Yeah, we know the age. Then we can see if it's a periodic sampling, then every Ti step it will do the sample, so it's a zigzag, like, yeah, it looks like this in this case. So similarly, for the base station, the UBIT, is the UBIT is the generation time of the sample from source node I that is currently maintained by the BS at time slot t. And we also have this age of information of the base station. Then we will have this, they talk about the connection, the relationship between the base side and between the base side and the source node side. For a sample, for the k sample, they define the beginning transmission time slot BIK and the ending time slot EIK ending. So for example, if we start transmission at here B and finish and at this at here, then because it takes one time slot to transmit to the base station, so here now it's BIK plus 1. So here they transmit the K sample to the base station, then the UIB will take this one. So it's the definition, and also we get this connection between the base side, the AOI of the base side and the source node side. And we have this formula to show this to show the curve of this ABI over the time step t. If t is the ending time slot, then it will update the information, update the age of information by this formula. Otherwise, it's just plus 1 through the previous time step. So they give this example. If a node I sample k at here, and we can see the age of S, the base station, the age of base station. We can see the table. In the table, they show how these values are changed over these different phrase. If they begin to send the k, how they affect the values, and now they generate a new k at this time step, so the age of information is updated to 0. And when the transmission ends and go to next step, next time slot, then the base side is updated. Previously, it's always equal to the k subtract 1. Now it's TIK. It's a very simple case to show the to explain this formula and the relationship of all concepts. So based on this formula, based on this one, the target of the scheduler algorithm is to make the average age of the information of the base station side minimum. Yeah, they want to minimize the average AOI, which means because this one is the time step of t. So for a long term, we start from time step from t equal to 1 to t. then it's long term, and we maybe we can consider the t goes to infinity. Then the long-term average of the source node is source node i's AOI at the base station level is can be written like this one. It's the average of the different time step. Here t from 1 to t, and it take the average. Then it's for a single node. Then the overall source node at the BS is defined like this. First, we need this WI. It's the weight or the priority of the source node's i's information. Some nodes will have higher information, higher priority. It's more important, so it needs a W. So the AOI over all source nodes at the base station is equal to this one. It's the sum of all nodes. And the target, the object, is this term. Then the author defined the scheduler, because we need the scheduler for the base station to do this transmission over all source nodes. For a base station, basically, it's source limited. It only has m data units available for transmission in each time slot. For n nodes, we have n nodes. So the xt at this time slot is n vector, where xit element is the number of data units that is allocated to user or node I at the time slot. So the sum of this vector is less than or equal to the m, because it only have this data units. So the goal is to find an optimal scheduling algorithm, so that the overall age of the information can be minimized. And for this, they found these properties for a optimal scheduling algorithm. If under the arbitrary sampling, under the case of arbitrary sampling, there exists an order-based scheduling algorithm that can achieve the optimal object. But because arbitrary sampling will be more difficult, when each source is sampled periodically, then we can find a cyclic scheduling algorithm that achieves the optimal objectives. And the authors also show the performance bounds. They derive this performance bounds. For this case, for the case of the per time slot sampling under the finite link capacity, we can see this is a very complex formula. It means the average AOI at the BS is proportional to the W, the priority, times the size of the information, size of the sample, and also the W. It's we can see it's I to k and k plus 1 to n, but it's have a very small difference. Another case is the arbitrary sampling on the infinite link capacity. Here m equal to infinite. In this case, they derive the result is that the lower bound, the optimal object, is this one. It's the sum of the average AOI at source node side plus 1. Source side plus 1, and take the priority and take the sum. So based on the lower bound, they design a scheduling algorithm for each time slot t. For each time slot t, they first they do these operations. They complete the transmission of the uncompleted sample, because if it's uncompleted, the sample must be finished transmission at first. Then, if it's finished, then among all, they will find the node I with the largest value. Then, if this node have this size, if the size is less than or equal to the number of remaining transmission units, the units remaining of the M, then they complete the transmission of this sample. Then they find next node, go to step 3. But if the Li is greater than the number of remaining transmission units, then transmit this sample in completed part with all remaining transmission units, and goes to step 2 and to finish the transmission. So this is a very simple scheduling algorithm. Final part is the simulation experiment. You can see they have these simulation parameters, different W, L, T, unit, N. The result, they show that if the link capacity, the base station have stronger, more unit to transmit, the age of the information will be smaller. They don't need to wait too long. And if the sampling period goes up, the overall AOI goes up. And they show this, their algorithm is very close to the theoretical bound. And if they increase the sample size and the number of the source nodes, it also increase the AOI. The final one is they compare the async configuration and the async configuration and the sync configuration. We can see the async configuration is closer to the theoretical lower bound. It's better than the sync case. So they showed all these results. Let's give a conclusion. This paper, it generalized 3 key concepts in this research: sampling behavior, size, and the transmission capacity. They show 2 interesting properties of the optimal scheduling algorithm, and they derive the theoretical lower bounds. And they develop this scheduling algorithm, and they show in the simulation the algorithm has a very close performance to the theoretical lower bounds. So that's so this is my presentation. That's all. Thank you.